Okay, folks, this is probably the hardest related rates problem you'll see unless you choose to do the optional assignment, which you should. But this one is pretty tough, so I'm going to urge you to dig in right now. So make sure you're in a good spot to really listen to this video, watch it all the way through, and take good notes. I think you'll be able to follow it, but I think you'll have to make sure that you're putting in your maximum amount of attention in order to follow this. Okay, we're going to follow the same steps as we have in all of our other examples. So the first thing we're going to do is draw a sketch, and here we're talking about a cone. So a cone, you guys are familiar, looks like this, right? And yours probably looks nicer on your paper because drawing on the computer is hard. The height of the cone is increasing at a constant rate of 6 meters per minute. So I'm just going to annotate as we go. And the volume is decreasing at a rate of 301 cubic meters per minute. Okay, so pause for a second. So we have this cone, it's getting taller, but the volume is getting smaller, right? And we're going to end up looking for the rate of change of the radius, right? So we're looking at the radius. So if the cone is getting taller and the volume is getting less, the volume is decreasing, that means that radius has to be decreasing as well. Because if it's getting bigger this way, but it's overall getting smaller, we would expect that this radius is getting smaller. So hopefully that's what we find out. It gives you the volume of a cone formula, which you may or may not have known, 1/3 pi r squared times the height. And it tells us what's the rate of change of the radius. Okay, so we draw a sketch. We're going to write an equation. So our equation is going to be that volume equation. Then we're going to differentiate with respect to time. So our next step is the derivative. And remember, all of our variables, and pi is not a variable, all of our variables are functions of time now. So the derivative of v is dv dt. 1/3 pi is a constant, so I'm going to go ahead and pull those out right away, I think. And then we want the derivative of the inside now. So we want the derivative of r squared times the height. So these are both functions, so we're going to do product rule here. So 2r, and chain rule, right? So dr dt, because r is a function of time, times h. So that's the derivative of r squared times just plain old h. Now we want the derivative of h times just plain old r squared. So r squared stays the same, and then we have dh dt. Okay, so there's my derivative. And make sure you know how I got that. So pause for a second. So I use product rule, right? So product rule, remember, is the derivative of one function times the original other function, and then vice versa, right? So g times f prime. Okay. Once you're clear on how we got that, we're going to move on. So our next step is going to be to substitute and solve, right? So we need to find everything that we know in the text. And I'm just going to make a list in this case because there's quite a few variables happening here. So we have the height of the cone is increasing at a constant rate of 6 meters per minute. Okay, so that's dh dt is 6, positive 6 because it's increasing. The volume is decreasing, so dv dt at a rate of 301 cubic meters per minute. Okay, negative 301 is the decrease. And then moving further in the text, the height of the cone is 7 meters. So no changing happening there, right? It just says the plain old height of the cone. So 7 meters is h. The volume is 566 cubic meters. What is the rate of change of the radius? Okay, so what is the rate of change of the radius? That's a good thing to note at this point when we have a lot of variables. So that means what we're looking for is dr dt. So that's what we're trying to find. So we're not going to have that to plug in. But notice we don't have enough variables yet. So I have dh dt, I have dv dt, I have h, and I have v, but v doesn't show up in here. We need an r, right? So before I start substituting in, I have to figure out what my r is. And this is sort of like our Pythagorean theorem problem. So I need to find my r. And to do that, I'm going to use my volume formula. And I'm going to plug everything in. So I get 566 equals 1/3 pi r squared times my height is 7. Okay, so I just plugged in what I knew to my volume formula, and I'm going to solve for the radius. And to keep this video a reasonable length, I'm going to trust that you can do that. Make sure you can do that though. So check my answer here. I get r equals 8.787. And I rounded that here, but try to keep several digits for accuracy. Okay, so I solve for r now. And now I have everything that I need to start making my substitutions. Okay, so dv dt, we're going to go just straight across. dv dt is negative 301. 1/3 pi is just numbers, right? 2r is 2 times 8.787. dr dt is what we're trying to find, so we're leaving that in. So it's useful to note that, right? Because otherwise I'd be looking through all my variables to try to figure out what it is. H is 7. Plus r squared. So r squared is going to be that 8.787 again squared times dh dt, which we have is 6. So now I have an equation, and it's kind of an ugly equation in this case because of all these decimals. Now I just need to solve for what I'm looking for here. So dr dt is what I'm interested in. And this is something you know how to solve. So this would be just combine my like terms, work very carefully because there's a lot of opportunities to make mistakes, and isolate that dr dt. I'm going to give you a hint on these, especially for these problems involving pi. When you can, try to avoid distributing it. So like I think a lot of you would think like, okay, I'm going to distribute 1/3 pi across the parentheses. That's a fine move, but the easier move is actually to divide to start. So 1/3 pi, I'm going to divide on both sides. And my work ends up coming out cleaner. So when I do that, I get negative 287.44. Okay. And then I will just multiply these two together. So I'm going to do 2 times 8.7 times 7. And I get 123.02 dr dt. And then I'm going to multiply 8.787 squared times 6. And I get 463.28. Okay. So now, you guys know how to solve this. I'd subtract 463 on both sides, and then I divide by 123.02. Okay. And what you get when you do that is negative 6.1. And I'll keep a couple more digits. Negative 6.102. Okay. And that would be, so it is a radius that is changing, so that is just going to be plain old, what were my units in the original problem? Meters, so plain old meters per minute. And remember we said we would expect that the radius should be decreasing based on the height increasing but the volume decreasing. And sure enough, our derivative here is negative. Alright, so that's consistent with what we would expect based on the text. Alright. So make sure you've captured this in your notes. On these, work carefully and follow this as an example. You'll get a couple different formulas, but like the harder ones, the key is always this step where we had to find the radius. So right here where we had to plug in what we already knew to find another variable, that is the trick here on all of these.